as they feel. Standing room only now. It's very popular. You ready? Right, today we're going to look at updatable text fields using binary data. Some of you will know this as shift registers, others of you will know this as CSR, custom shift registers. What it actually means is we're going to do updatable text fields using binary data. So, what is binary data? We all know that we count various things, like in hex system, base 16, we start at 0, we get to 9, we carry 1, no we don't here, we go A, don't we? We go F, then we carry 1. In the decimal system, we go 0 to 9, and yes, here we do carry the 1, we get to 10. In the binary system, we have 0 to 1, and then we carry the 1, so there's two things there. So that's the binary system. In our coding, we have things that are called bytes, and we have bits. A bit is just the switching of the transistor either on or off. A byte consists of many more bits. So a byte consists of many bits, and they are 8 of them. So another two things that we're going to be using. There are different ways to communicate between a controller and a printer. We can use Ethernet. We can use RS-232. Remember, that's recommended standard 232 of the IEEE of the USA. And we can use a new way which we're going to investigate, sending in binary data. Now, with RS-232, we know the speed at which we're going to be sending data down this line because we've set it to a baud rate, something like 9600, and you've set both sides to 9600. Ethernet's a bit more technical, but it's done by the network itself, and it could be something like 10100. It can also speed up, slow down, it depends on the network and what's happening. Binary data, on the other hand, is slightly different, as we will see. When we're sending binary data across, we are sending a series of bits. A bit is either low, when it's 0, or high, when it is 1. Low when it's 0, high it's 1. And it can carry on as another 0, and as well you can have lots of 1s. So it depends on the pattern that goes across. This data, if it's sent across from a controller to a printer, like that, the printer would not know what speed that data is going, so it would not know how to interpret it. We can't set a baud rate or a bit rate on this side or on this side. So what we have to do is we have to send the clock signal with it. So our clock signal will be going along with this in a particular pattern. We'll see in a minute how to work it out. So it has a clock and it has data. This is the bit that sets the speed. The baud rate, the bit rate, depending on what we're talking about. The data bits go across. Now, in RS-232 you have something in here called a UART, which takes the data and sends it into the rest of the printer. Here we don't have that. We have a more basic system, exactly what the UART might be doing, but here we have what's called a shift register. The shift register is nothing more than, if we think of it, a box with different sections in it. When the data arrives at the box, the clock signal goes up, the data goes into the first box. The clock signal comes along the next one. Each time the clock signal is seen by the printer, the data moves one across. So the one moves there, that could be a naught, as we've got here. Then it moves across one more until all the data is into the shift register. Once it's in the shift register, in our printers, the shift register is housed in the FPGA. Could be housed anywhere else. That data is in there, and that data now comes out and is used by the printer. But how do we now work out how to send data in, and how do we work out the clock cycles for this? So most of you, I think, will be working with a very large customer which we have, who uses this. Not the only customer we have that uses this technology, but this is our biggest customer. We still have a lot of customers using the very old technologies that we had, the A series, with this shift register stuff, who haven't migrated to any other domino printer yet. So they're going to make the jump to AX. That's why it's important this works not just for the big customer, but for all the other little customers as well. Our big customer says that he wants us to have the high pulse for the one to be 1 millisecond. That means that the low pulse, the other part of this period, is also 1 millisecond. So the clock signal for that customer is going to be 1 millisecond high, 1 millisecond low, and that gives us, in 1 second, that will give us 2 milliseconds used for there. If we take 1 second to 1,000 milliseconds, we divide it by 2, it will give us a frequency of 500 Hertz. So that means we can get 500 bits into the printer every second. Frequency is number of times per second. So to get 500 of these bits into the printer per second, we need to have this clock cycle. When you go to start testing this, you need to be sending a clock cycle that is always accurate on how it works. So together with that, you'll then send some data. For the particular customer we have in mind here, he's been a bit creative where the custom part of the custom shift register comes in. We gave him a shift register that is either 5, 6, 16 or 32 bits long. This customer decided that he would use it at 32 bits in most of his machines. Some of the very old machines are still 5-bit, some 6-bit or 16. That means you can have in here 32 bits, so you go from 0 to 31. Now if you wanted to print something like how many days in this month, the largest character he's going to need is 31. I'm not saying this month has 31, but the largest number of days in a month we have is 31. If you put down 31, you'll find it is a 5-bit. That isn't the number 31, but it's a 5-bit number. It has leading zeros on it to make it up to its 8. But we can get rid of the leading zeros and we say we have 5 bits. You'll never go higher than 31. So he's decided that he would have this register that he's going to send in divided up into items of 5 bits wide. I'll make a small one here for a particular reason. So he would have in here something like an event, or he'd have something like a jaw ID, whatever these names are, but they will only ever be 5 bits long. Apart from one of them, which is the serial number, which is only ever going to be 1 bit. But you can divide it up as you like. Okay, so the printer doesn't care about this because we have our clock signal, we have our data, the data is going off to the printer on this side. The clock signal is clocking it into the shift register inside the printer, and it all gets in there, all 32 bits of it. Then this is copied into a software buffer. And I use the term software buffer because we can't get hold of it when it's in the FPGA very easily. So we copy it into the software. Eventually it goes into what I call the print system buffer. So we have a label here. The label can get the data from this print system buffer and it can print it. That's why it's an updatable text field. Because we're going to copy this stuff down into the print buffer and then put it into the label. So, how do we get it down into that part of the system? Inside our label, we can have logo, we can have A, B, C, X, Y, Z, and over here we want to have something called the drawer ID. The drawer ID is the identifier of the item that's closing the carton the juice has gone into. Okay, that's the jaw. We normally have a rotating section. You have your tube going down here. This crimps it and folds it and stamps on the drawer ID of this one. You normally have like 10 jaws around here. If you find one of your juice cartons leaking and it's number 3 all the time it leaks, you know to come and fix number 3 only. So it helps the manufacturer of the cartons know which one to fix. So this drawer ID, it needs to get its data from here, and say we want to get it from this section over there. How does it get this from there, and how does it make that into what it needs to make this? This is only for this particular customer. As we know, it's a big customer. They have here a Lua script, and this will be something like drawer ID.NUA. So you make your label, you put your Lua script in there. Inside the Lua script, the first thing it does when it runs, and it runs at the print go, it grabs the whole of that buffer. Inside there it's been told to shift this left, right, until it gets just that section of data in there. So the Lua script then knows it's 101010. It then needs to go and look this up in its table, or it needs to make that binary number into a real number. If it was, for instance, there, we would know that that is jaw 2. So we would print 2. Binary, that makes it 2. So in your next to the ABC would come the word 2. Some of them have to go and be looked up from charts. Things like the events. The events come out as a number. The number then needs to be equated to a particular event. And they normally have their events like something A to Z. Because there's 31 of these things. They also use things like equals, hash, or stuff like that as well. Those are in the tables that go with it. So, we know we send the data in, we send data and a clocking signal. We get the data to come down into the print buffer. We know we've got a second section, that's this label. We make a label, we put a Lua script in. The Lua script has the data which it got from the print buffer, and it prints it into the label. So that is, in a nutshell, how we get data into the label from binary input. You can ask questions now, either on camera or off camera, if there are any.
Is this quite an old technology then?
It is very old.
Moving away from it.
Yes. Next week we will go over the new technologies that's taken its place. But we've still got a lot of this out there. This customer is not going to change all his old machines, the big filling machines.
So what's the limitations of it then? Why would you move to a different technology?
Speed.
Just speed.
And you can only get 32 bits in here maximum. So if I want to put a long sentence in, I can't. And it's very slow, it's 500 hertz. You can, at 32 bits, you get about 15 messages per second as your maximum rate. We can go a lot higher than that. This is only 4 bytes in total. If you take it 32, each byte is 8, so you get 4 bytes in here in total. I can print more than 4 bytes a lot faster than that with other methods that we have. Now, one of the other questions that you may be saying is, how on earth do you get this to work if you're going to test it? Because you've got a clocking cycle which you've got to tie up with the data. The answer to that is, you need to have, what we're using is mission control. If you haven't got mission control, make some inquiries about getting it. There is also a National Instruments one that I've not used that does a similar thing, but you've got to make sure that it does the right thing to get the right data. The mission control, we know it does it because I wrote it, me and Edsko wrote it, so we know it does the job we need it to do. It's easy to use.
And when is the mission control version 2 available for use?
Tomorrow is the day they start to populate the boards, I believe, I was told this morning.
Okay.
So within a week or two, everyone should have, who's ordered one or got one or whatever, a mission control on their desk. So, there we are in a nutshell.
Who do we order that?
What's his name? Chris Jiggins. Right, stop the recording.
Any more questions?
Everyone's happy?
Thanks a lot, Stephen.
Thank you. That was a